I'm going to present some results obtained with the RIBRAS facility based on reactions induced by the helium-6 exotic nucleus. Here is the outline of my presentation. First, I'm going to talk a little bit about the motivation to study nuclear reactions in general, and then I will present some evidence of the first evidence of the exotic nuclei. And in this point, I'm going to present some properties of this kind of nuclei and the methods for production this kind of nuclei. And after this, I'm going to talk specifically about the RIBRAS facility installed at the University of São Paulo and allow us to study this kind of nuclei. And then I'm going to present the research program developed in the last years since its inauguration at the University of São Paulo. But here in this point, I'm going to focus on the helium-6 elastic scattering in the reactions. And to finalize my presentation, I will present some conclusions and future plans. I'm going to start my presentation asking a question. Why to study nuclear reactions? First, this study allows us to understand the internal structure of the atomic nuclei. And with this, we can understand some different reaction mechanisms that occur when we have a nuclear collision, and enable us insights into nuclear process occurring in star and cosmic events, contribute to theories about the origin and the evolution of the universe. And besides this, this kind of study enables us to understand the production of new isotopes and the elements that have a lot of applications, like in medicine, arts, archaeology, industry, in this case, specifically in technological advancements. So the nuclear reactions study is a large investigation area and have a lot of applications. So in 1980 years, the experimental situation changes a lot because in this time, big national laboratories like RIKEN, GSI, GANIL start to produce radioactive ion beams. And with this facility started a new kind of investigation, new kind of experiments. And it specifically in 1985, in 1985, Tanihata published a paper based on lithium-11. There was a significant milestone in nuclear physics because in this work was observed that this nucleus, the lithium-11 nucleus, shows a large values of the radius in comparison to its isotopes, as you can see here in this simple picture. Here we have the size of the lithium-6, a comparison of the size of the lithium-6, lithium-7, lithium-8, lithium-9, and here the lithium-11. So the size of the lithium-11 is comparable, is similar to the size of the lead-208. So of course, the usual equations of valid for stable nuclei is not valid for this kind of nuclei. So this kind of nuclei presents an unusual distribution of nuclear matter. So presents an extended matter distribution. And here I show you a picture where you can see the radius as a function of the mass of the lithium isotopes, and you can see the radius of the lithium-6, lithium-7, lithium-8, lithium-9, and here the lithium-11. So this discovered opened up new perspectives for studying nuclear structure and the properties of this kind of nuclei. So when there is a distribution of nuclear particles beyond the typical range of a nuclear force, here, we have that we said a halo effect, or else you have particles around the nucleus which significantly increase its radius. And another important effect is the Brownian condition of this kind of nuclei, is the Brownian condition, and the Brownian nucleus is a system composed by 3 or more nucleons that when we remove one of the nucleon of this system, the entire system becomes unbound. And this concept is analogous to the Borromean rings in mathematics, but here the rings is the binding. And here I show you some two examples of the Borromean nucleus. The first of one is the helium-6, composed by helium-4 plus 2 neutrons, and another one is the lithium-6, composed by lithium-9 plus 2 neutrons. And when we remove one neutron of the system, the remaining system is unbound. So the helium-5 is a not bound system, as a lithium-10 is a not bound system. And here I show you the Euclid chart. There is the field of study of nuclear physics. And as you know, the light stable nuclei has an amount of protons and the neutrons that when represented then in a diagram of protons versus neutrons, they are concentrated here in this region called stability line. When the mass increases, this stability line inclines during the Coulomb repulsion, and far from the stability line, you can find the exotic nuclei. There is a nuclei with excess of protons or neutrons, and as a consequence, they have very different properties in comparison to stable ones. Nowadays, we know about 300 stable nuclei, as you can see here by black squares, and a lot of nuclei far from stability line, as you can see here by yellow color. This green region is the nuclei not observed, but foreseen for different nuclear binding energy theoretical calculations. And here, I show you a picture where you can see the evolution of the discovery of the nuclides over the years. And I would like to bring your attention for the contribution of the proton-rich and the neutron-rich nuclei. There is an exotic nuclei. And you can see here by purple color and by green color. So the exotic nuclei, this kind of nuclei have a very big contribution in this scenario. And this study of the exotic nuclei as a large investigation area sizes light nuclei until super heavy elements. And other properties of this kind of nuclei, as I said before, an exotic nuclei in general are far from the stability line, show different properties from those of stable nuclei. For example, present an excess of protons, and in this case, we said a proton-rich nuclei, or present an excess of neutrons, and in this case, we said a neutron-rich nuclei, present low binding energy, half-lives that can vary from days to minutes to microseconds. And here, I would like to compare the binding energy for stable weakly bound nuclei and for an exotic nuclei. And it's important to take in account to remember that for stable nuclei, the separation energy for protons and neutrons is around 7 up to 10 MeV. And here, in this first table, we can see the binding energy for the lithium-6 in this configuration is only 147 MeV. It's a low value, but when we look for an exotic nuclei, for example, for boron 8 in this configuration, the separation energy, the binding energy, is only 0.137 MeV. The exotic nuclei presents a much lower value for binding energies in comparison to stable weakly bound nuclei. And I would like to finalize this part of my presentation asking a question. Why study nuclei outside the stability line? Why is important? Why is interesting? The importances are many. First, you can answer this question thinking about another question. What are the limits of the atomic nucleus? Or else, how far can you add protons or neutrons into the nucleus and the system stay bound? And this kind of study is interesting in order to test nuclear models under extreme conditions of isospin and very low binding energies, because the nuclear models were developed based on data from nuclei near the stability line. Another important question is, how does nuclear structure depend on isospin? And another thing is new phenomena like neutron or proton halos that appear near the drip lines. And it is important, this study is important for nuclear astrophysics and have a lot of applications like production for radioisotopes for medicine. And okay, it's interesting to study nuclei outside the stability line, but how to study this kind of nuclei? In order to study this kind of nuclei, we need to produce these nuclei. And to do this, we need high-intensity accelerators with 10 up to 12, 14 particles per second. And you have two methods to do this. The first one is the projectile fragmentation. And here, the primary beam delivers from the accelerator, collides in a thin production target, and this collision produces a lot of particles, including the radioactive particles of the interest. And these particles passing through a selection system in order to give us a radioactive ion beams selected in order to perform the experiment. And another method is the ISO method, and the primary beam delivers from the accelerator. Now is stopped by a thick and hot target, and the radioactive particles that are produced in this collision are sent by diffusion to the ion search, and here the particles will passing through a selection system, and they are reaccelerated in order to give us a radioactive ion beam selected. And here I show the laboratories around the world where enable us to study this kind of nuclei. And here you can see the RIBRAS facility is the only one facility in South America. And this facility is installed at the University of São Paulo, and it works together a Pelletron accelerator. And here we have the picture of the major facility for nuclear physics research in Brazil. And here we have the schema of this facility. There is a HMV tandem accelerator that provide primary beam like these ones from 3 up to 5 MeV per nucleon. And here we have the ion search, the control room, and the experimental area. And here we have the RIBRAS facility. And here I show you the evolution of the radioactive ion beams in Brazil facility over the years. This facility was installed at the University of São Paulo in 2004. And here we have a picture from this time, from 2004, another picture from 2011, and here another picture from 2015. Nowadays, in the present, the visual of this facility is the same, but since 2022, we are making efforts in order to improve the data acquisition, and we installed a new digital electronic device in this facility in order to allow us to perform exclusive and coincidence measurements using large area detectors. So, as you can see here, the RIBRAS facility is composed by 2 superconductor solenoids that are able to select light secondary beams of nuclei far from the stability line. And before the first solenoid, you have a small scattering chamber where I produce the radioactive beam. And between these 2 solenoids, you have a scattering chamber that you can use to perform experiments. And after the second solenoid, you have a big scattering chamber that you can use to perform experiments. And this region, the first scattering chamber, you can see with more detail here in this picture. And here we have a schema for this part of the canalization. And here we have the primary targets where I produce the radioactive secondary beam. And as a primary target, we can use solid or gas targets. And the primary beam delivered from the accelerator collides with these primary targets, and this collision produces a lot of particles, including the radioactive particles of the interest. The particles in this angular range will be accepted by the solenoid, and just after the primary target, you have a Faraday cup that you use to stop the primary beam and measure the intensity. And of course, the secondary particles in this angular range is from 0 up to 2 degrees will be stopped by the Faraday cup too. And after 6 degrees, we have some collimators into the canalization doing the bore of the solenoid. So this particle in this angular range will be accepted by the solenoid, and these particles will suffer a selection system based on magnetic rigidity according to this equation. And here I show you an example of the selection of the solenoid when you use only the first solenoid, because you have 2 scattering chambers, so this system allows us to perform experiments using only the first or using both solenoids. Here is only one example when we use only the first solenoid. And in this case, the detection system is organized inside the middle scattering chamber. And up to now, the detection system uses telescopes formed by silicon detectors as a detection system. Here I show you the production reactions that you usually to produce using the RIBRAS facility and the respective intensity of the secondary beam, taking account a 300 nanoampere electric primary beam. So we are able to study helium-6, lithium-8, beryllium-7, and the others. And as I said before, the RIBRAS facility is composed by 2 superconductor solenoids, and you have a small scattering chamber located between the both solenoids, and another big scattering chamber located after the second solenoid. And here I show you the comparison between the result that we obtained when we performed the experiment using only the first or using both solenoids. In the both cases, the idea is to study the helium-6 projectile. And in this case, to produce the helium-6, we usually use the lithium-7 primary beam and the beryllium-9 primary targets. And in this collision, produce a lot of particles, as you can see here. And besides the solenoid selection, we have a 2-dimensional spectra with some contaminant particles. But it's not a problem, because these particles is clearly separated. And so this is a typical 2-dimensional spectrum obtained here when you use only one solenoid. But depending on the experiment, it's interested to purify the secondary beam. And in this case, we performed the experiment using both solenoids, because the second solenoid helps cleaning the secondary beams, and in this case we use a degrader here positioned inside the middle scattering chamber in order to change the magnetic rigidity of the particles with different atomic masses. And as a consequence, you have a much secondary pure beam, as you can see here in this 2-dimensional spectrum. Now I present the scientific program developed using this facility. ⁶He is an inauguration. So the main studies is based on elastic scattering measurements induced by radioactive and exotic nuclei on light, intermediate, and heavy mass targets. Besides this, we perform some transfer reactions and some resonance scattering. And now I present some results obtained ⁶ inauguration, but all of them induced by helium-6 projectile. And the first of one that I choose is the helium-6 plus aluminum-27. It's the first result obtained with the RIBRAS facility, the first experiment. And the black points are the RIBRAS data, and the solid line are the optical model theoretical calculations performed using the Paulo potential. And for this system was observed that is necessary only normal values for the imaginary normalization and for the diffusionists in order to give us a good agreement with the experimental data. So indicating that no effect of a breakup coupling for this system. But when we increase a little bit the atomic mass of the targets, we have a different situation. Here we have a comparison for helium-6 is the black points in comparison to the helium-4 is the triangles obtained with the RIBRAS facility. And for this system, it was observed there is necessary large values for imaginary normalization and for the diffusionists in order to give us a good agreement with the experimental data, indicating an effect of breakup coupling. And this both analysis was performed 20 years ago. After this, we started to perform using a more sophisticated calculations. And here I present you some calculations performed using 3-bore and 4-bore CDCC calculations. The first of one is the helium-6 plus beryllium-9. There is a calculation without free parameters. And for this case, the dotted black line is the calculation without include of the continuum, while the red dashed line are the calculations, the 3-bore CDC calculations, and the solid blue line is the 4-bore CDC calculation. So we can observe for this light system an effect when we include the breakup coupling. And in particular, for this light system, the couplings to the nuclear breakups are important. It was observed that is important. In contrast to this heavy system, here we have the result at 4 different laboratory energies for this heavy system, the elastic scattering measurements. The black points are the RIBRAS data in comparison with 3-bore and the 4-bore CDC calculations. And here we have one of these energies with more detail. And the dotted blue line is the calculation without including the continuum, but when we include the nuclear coupling, we have here the dashed red line. But in contrast with the light system that I said before, for this heavy system, we observed that it's necessary to include the Coulomb and the nuclear coupling in order to have a good to observe a good agreement with the experimental data. And here we have the same situation for this intermediate system. Here we have the results for 3 different laboratory energies, and again, we observed an effect when we include the breakup coupling. So I show you now the several systems induced by helium-6 projectile in light, intermediate, and heavy mass targets. And except for the aluminum-27, all of them, it's important to include the breakup couplings. So with this in mind, why not? Why only for aluminum-27 is not important? With this in mind, we propose a master project for Igor Arruda, based on in order to verify this no effect on the breakup coupling. Now using this new digital electronic device that provides us more capability, more data capability. And here we have the 2-dimensional spectra obtained for gold and for aluminum-27 targets. This is a work in progress in the group now. And here we have the preliminary results, and the black points are the elastic scatter angular distribution compared with 3-bore and 4-bore CDC calculations. There is the blue and red lines. The dashed line is the calculation without including the continuum. But here is the very, very preliminary result, because we observed that when we change the core target potential, there is a gradient for the CDC calculations, we have another result. So in this moment, we are investigating the dependence of the alpha aluminum-27 targets in the CDC calculation. Because here, for this, in this case, we use a potential alpha aluminum-27 from the literature, and you have a very beautiful, excellent agreement with the experimental data. But when we change this potential, we have a very different result. So we are investigating the dependence of this potential in this calculation. And another work in progress in the RIBRAS group in this moment is the helium-6 plus natural zircon elastic scattering measurements and the reactions. And the idea of this work is only to study a collision with a target not explored yet. And here we have a 2-dimensional spectrum obtained with zircon and obtained with a gold target. And the black points are the RIBRAS data, the elastic scatter angular distribution. Here, compared with the optical model calculations, it's only a fit. And here, compared with the 3-bore CDC calculations. Another work is the helium-6 plus vanadium 51. And the idea of this work is based on this paper, where we can verify, we have this picture on this paper, and we verify. Here we have a relation between the total reaction cross-section of the helium-6 related to the lithium-6 as a function of the mass of the target, and you can observe a decrease for aluminum-27 targets. And after this, you have this region without experimental data that require additional information. And with this in mind, we propose the master project of Jonathan Narvaez. And we perform a new measurement at this laboratory energy. And here we have the vanadium two-dimensional spectra and the gold target spectra. And the black points are the RIBRAS data in comparison with optical model calculation. It's only a preliminary result, it's only a fit. And what you can learn from elastic scattering measurements. One thing that you can extract from this kind of study is the total reaction cross-section. Here I present you a systematic obtained from elastic scatter measurements. And in order to compare different systems in a same picture, we calculate the reduced reaction cross-section and a reduced energy that remove geometrical effects, allow us to make this comparison. And I separate here the graphs into the mass of the targets, and here we have the results for beryllium-90 targets, and here for aluminum-27 targets, for medium mass targets, and for heavy targets. And for all of them, we can observe that the system induced by radioactive projectiles presents a higher value of the total reaction, the reduced reaction cross-section. And which are the reaction channels are responsible for this enhancement? With this in mind, we can try to understand the alpha production, because when we perform an experiment using the RIBRAS facility, for example, induced by helium-6 projectile, we have a two-dimensional spectrum like these ones, and we can observe a large yield of alpha particle. Here we have elastic peak, the helium-6 elastic peak, and below the elastic peak, we can see a large yield of alpha particles. So these alpha particles could be from several processes. For example, the breakup of the the breakup of the projectile, or the breakup or transfer from the projectile to the targets. For this light system, we have a more complex case, because here we have the beryllium-9 as a target, and the beryllium-9 could break into 2 alpha particles. But for this heavy system, a complete description we can find here in this paper. And here you have the energy and the angular distribution of this yield of alpha particles, compared with a lot of calculations. For example, here the dashed black line is the 3-bore CDC calculations that represent the breakup of the projectile. But for this heavy system, this was observed that these alpha particles mostly result from the 2-neutron transfer, as you can see here by blue line. And we extended this work, this idea, to light and intermediate mass targets. And here we have the result for the energy and for angular distribution of these alpha particles observed in this collision. But here, as I said before, have another additional complication, because the beryllium-9 could breaks into alpha particles. So these alpha particles could be from the breakup of the projectile, transfer from the projectile to the target, and the breakup of the targets. And this collision, this measurement was performed using only the first solenoid of the RIBRAS facility, or else we have a secondary cocktail beam. So in order to perform this analysis, we take in account the contaminant beams, the contaminant particles inside the secondary beam too, because these contaminant particles could break the beryllium-9 too. And here we have the results. We perform a lot of calculations, perform CDC calculations in order to take in account the projectile breakup, the no-elastic breakup, in order to take in account all processes besides the elastic scattering. And we take in account the fusion contribution, and the 4-bore CDC calculations in order to take in account the breakup of the targets. And in order to sum all of these theoretical calculations, we consider the contribution of each particle inside the secondary beam, or else we perform a weighted sum, taking account here the contribution of each particle inside the secondary beam. And here we have a result. And for the lower energy, because here we have for two different, of two different laboratory energies. And for low energy, for example, here we have the total reaction cross-section that you can find at the literature. And when we compare our results for the breakup reaction, including the elastic breakup and the total fusion, we can find a very similar result. There is an interesting result. And here we have the results for the aluminum-27, and here we have the gold target and the aluminum-27, where you can see the yield of alpha particle. With this yield of alpha particle, we obtained the energy and the angular distribution. And here we have the preliminary results, because as I said before, in this moment we are studying the dependency of the core target potential. So this is a preliminary result. And for the last one, for the zircon target, and here we have the two-dimensional spectrum obtained with the zircon, where you can see the yield of alpha particle, and here for the gold target. And here we have only the preliminary results for the angular distribution. The energy distribution are in progress. And here we need to include the CDC calculations. This work is in progress. And to finalize, I would like to say that the main research objectives of the RIBRAS group in this moment is to study in detail the reaction mechanisms of weakly bound cluster-structured radioactive nuclei with light, medium, and heavy mass targets at low energies. And in this moment, we are working in order to increase the detection capability of this system. And we installed a new digital electron device in order to enable us to perform exclusive and coincidence measurements using large area detectors. And I would like to finalize, said a low energy, large radioactive beam facility as RIBRAS can make competitive contribution in nuclear reactions studies. And here is the formation of this group in this moment, and I would like to thank you very much for your attention. What? Qual slide? 31.
Yes, 31 transparency, please, or this one, or maybe the previous one is better. What do you mean there by fuse in this angular, in the lower part, in the angular distribution?
What the question? The fusion?
What is the meaning of fuse there in this angular distribution? No, below, in the...
Aqui.
Yeah.
Well, we performed this fusion calculation using the pace for this system, and we obtained this result. What they mean of there's a very low contribution.
No, okay, it's very low, but the angular distribution pace?
Yes, we convert to the laboratory angle. Yes, in order to compare. Yes, I do the same thing on my helium-6 plus beryllium-9.
Evaporation should be symmetry about 90 degrees, so something. Okay, it's too small, but it's in the previous one is not that small. I think that there is another transparency. Okay, no, for me it's so strange.
Strange, yes?
Yes, because usually the angular distribution of the evaporation is symmetric about 90
degrees. As a result in the program, we will have the result in the 0 up to 10 degrees, and we make a distribution on angular by angular. We convert only this.
In the laboratory.
Okay. This.
Here we have the fusion too. There's another system. I don't know if it's for this. I don't know if you have fusion too. Fusion evaporation too. All of them we see we observed the contribution of the fusion.
This
Fusion
is
evaporation, yes.
Lubian, I think this is a nice discussion for the discussion session because it looks like this will extend. More questions? Tobias?
Yes, Ken?
Yeah, sure.
No, it's just a curiosity. You showed this distribution of the data, not here. I mean, you have helium-4, helium-6, and it's just something very naive. No, go forward. Yes, here. You see? I was just curious. I mean, you change your target from heavy one to light ones. And you see helium-4 for the aluminum is distributed for many energies.
Here?
Yes.
It's not. It's only. I think it's only the resolution of the detector.
No. But you see, there are points for aluminum target that
here?
A lot of points. Yeah, you see for helium-4. Just go to the aluminum down there.
Sometimes it's some reactions in the gold target. I don't know here. This line.
Yeah,
you said.
Nothing there, almost nothing, and in the figure below there is a lot of points.
Here, of course, is the reaction with the aluminum target, but here it's a very low in comparison to this one. So could be some reactions, but I think it's only a degrader from the beam. I don't know.
Okay.
Okay.
Let's see if there are more questions. We still have some time. I have a question then. You said 3-body and 4-body CDCC. This 3-body is 2 neutrons you take as a part?
Yes.
This is
in 3-body, we consider we have the G-neutron model, where we consider I think I have a picture here. We have helium-6 composed by helium-4 plus 2 neutrons, and the 3-body calculations, we consider these 2 neutrons as one particle. And we have, for example, G-neutron model, where we consider an effective energy of the bind of these 2 neutrons lower than the realistic value, because we have 0.9 the binding energy of these neutrons. And this model, we can use 1.6 MeV, a lower value.
Kelly, I understand the dineutron for the bound state, but when you're talking about CDCC, you're talking about the continuum, and this dineutron in the continuum.
I understand. Why is the 3-bar, the difference for 3-bar and 4-bar? Sorry.
Yeah, but in the continuum, this dineutron will be some 2 neutrons very far apart, and why do you treat them as one particle? So it looks strange for me that in some transparencies it looks as good as the 4-body CDCC. It's not so much different.
Yes.
Anyway, last question. May I, Tobias? Is there any other question? If not, then yeah. Is there? No? So it looks to me that you explored everything you could do with helium-6, right? Or
yes.
Is there anything else you could do?
No, there isn't anything besides the helium-6. But in this presentation, I focus on the helium-6. But we have performed the experiment with beryllium-7. I don't know if stay here. Performed boron 80. There is another thing. Yes.
That's the future.
Yes. No. Now in the present moment, another presentation. Yes.
Okay. Good. Okay. Thank you very much. Let's. Now we have nearby.